All right. So I've got some images up here on my TV here in the classroom. I know you can't see that, but I've figured out through trying to do this whole camera thing that I need this here to keep myself on track. All the images that I'm using, however, are going to be posted on Blackboard where the other materials were. So the first thing I wanted to look at was an image that should be labeled 10-1, and it's just showing us an entire oiling system, just a generic diagram of our oiling system and how that works. And we're going to kind of jump off from here and talk about the different components that make up the entire lube oil system. So ultimately, we've got a oil pickup tube. That's where our inlet into the oil pump is going to be. That pickup tube typically has a strainer on the bottom side of it to get out any large contaminants in the oil. So we're going to find that pickup tube at the very bottom of the engine in what we call the oil pan, also referred to as the oil sump or the lube oil sump. And inside of there, we're starting off at that pickup tube. That pickup tube connects directly to our oil pump and serves as the inlet to that oil pump. And typically, our oil pump is going to be driven off the crankshaft. There's a few different types of hydraulic pumps that are used for lube oil pumps and diesel engines, and we'll touch on a couple of the most common types of pumps later on. So ultimately, once we get oil to that oil pump that's being driven off the crankshaft, that oil pump is going to ultimately pressurize or send lube oil flow to what we call the main oil gallery. You may hear it referred to as the main oil rifle as well. But it is a passage, a circuit that runs from the front of the engine all the way to the back. And off of that main oil gallery, oil rifle, is where we're going to pull lube oil supply to lubricate all the moving components internally to the engine. So going off of that main oil rifle, one of the first places we can go is to the galleries that feed the crankshaft main bearings. So if you're following along, hopefully you can open up these illustrations as I'm using them on your screen. We've got part of the diagram right here in the center where we see 2, 3, 4, 5, 6, 7, and those are all passages that are connected to that main oil gallery that feed down to our crankshaft main bearings, kind of in a orangish copper color in this illustration. From there, the oil then typically will travel through another circuit that goes from the main gallery or the main journals on the crankshaft, main bearing journals. There is a whole circuit bored through the crankshaft that jumps oil over to the adjacent rod bearing journal. That's where our pistons connect and the connecting rod connects to the crankshaft. On the first day we looked at that crankshaft and I pointed out those lube oil holes in the crankshaft. From there we kind of hit a dead end on this branch of the lube oil circuit. once the oil has reached the main bearing journals and main bearings and fed over to the rod bearing journals, once those bearings are pressurized with our lube oil, ultimately from there the oil is going to come out around the sides, anywhere it can get out from in between that bearing and the shaft surface. So if we're talking, for example, the main bearing, once the oil is fed to that main bearing and pressurized to whatever system pressure is, that will also pressurize the circuit going through the crankshaft to feed that rod journal. And ultimately, the oil gets pushed out down the sides and out from between those surfaces and drains back down to the oil pan to start the cycle back over. So jump into our next branch off of that main lube oil gallery. We've got a few other places that oil is going from that main oil gallery. We have to get lube oil up to the camshaft, our rocker arms, the valve retainers, all the parts and pieces that are in contact with each other that move in the cylinder head. So we're up top now. So we have a circuit that branches off of our main oil gallery and feeds up to our valves, rocker arms, camshaft, injector, plungers, and in much the same way that we feed oil to the crankshaft, we send oil up to the camshaft and hit the cam bearing journals. They don't have those numbers in this illustration, but it's all the round sections of the camshaft. So we've got the lobes of the camshaft that also have to get lubricated, and we also have our camshaft main bearings. So we're going to send oil off the main oil rifle up to that camshaft and ultimately out to those rocker arms, where the rocker arms come in contact with our valves and any of the other components up there. We'll go further in depth in the cylinder head in the next video and talk about how we get that lube oil to those individual components in the cylinder head. So going back to the main oil gallery, some other things that need lube oil. All these branches are very similar in the way the lube oil gets to those parts and pieces. But one thing we need lube oil to is the turbocharger. If we have a turbocharger, or if it's a supercharger, however we're pressurizing the manifold to run boost. So we have to feed the bearings that are in that turbocharger. And that's going to be a branch fed, again, right off that main oil gallery. It's going to go through the turbocharger. There's a bearings that support the shaft that have the turbine and then impeller in that turbocharger. They're bearings much like what we see on the crankshaft or the camshaft. And in some cases, we use roller bearings in the turbochargers in more modern applications. But a lot of the times it's still journal bearings like we see on the crankshaft and camshaft. One other circuit off that main oil gallery would be our filtration and heat exchanger. which in this illustration, we can see it actually, the oil filtration heat exchanger is actually, in this illustration anyway, not being pulled directly off the main oil gallery, but instead we have a branch that splits off in two directions right off of the oil pump. So when oil is coming out at whatever flow rate that oil pump is producing, and we're actually splitting it off. One branch goes to the main oil gallery, the other branch going over to our heat exchanger and lube oil filter. That's also where I believe in this example we have a pressure. The pressure relief valve is on the other side there of the circuit. On the main oil gallery side of the circuit, we have a pressure relief valve, and we'll briefly talk about that a little bit as well. But our heat exchanger and our lube oil filter is going to come off that one of those main branches coming out of the oil pump. We're going to go through the oil filter and heat exchanger, and it's going to return back to our sump to provide cooler and cleaner oil for the oil pump to pull back through the system. So I'm actually going to switch over to my PowerPoint here now. We're going to get a little bit more detail into the different major components of the lube oil system. And the first thing, it kind of makes sense to start off in the oil pan, or sump as we call it in some applications, because that's where the main supply of lube oil lives. So we're down in the bottom of the engine, underneath the crankshaft. That's where we're storing all of our oil. That's what's going to determine how much oil capacity there is for that engine. But the sump or oil pan is a reservoir usually located at the base of the engine cylinder block or crankcase, enclosing that area. Oil pans are manufactured from cast aluminum, mild steel, in some cases plastics or fibers, like fiberglass type materials. The oil pan acts as the reservoir used to collect the lubricating oil, which gravity causes to drain back down once we've lubricated all of our components internally. And so just gravity's returning all of our lube oil. And then it recycles back through the system. Dipstick, that's where we're going to check the oil level. That dipstick protrudes down into the oil pan or oil sump, and it's a way to see what the oil level is. Usually the oil level is checked with engine shut down. You may, in some applications, get a lube oil level while running. It just depends on if the manufacturer of that particular engine wanted to give us that information, because it may be useful to know that. You may not want to shut down to check the oil level. But if we're talking an engine like maybe some of our gensets, smaller engines that we'll see, you want to, before changing lube oil, you'd want to run it. So we get all those contaminants, carbon, any dirt, debris that has made its way into the engine, ultimately ends up suspended in the oil. So when changing lube oil, if possible, you want to get it up warm. I wouldn't say it's necessary to get it up to operating temperature, but getting some heat in it, getting it moving around and warm. So all those contaminants are suspended within the oil, so that when we get rid of that old lube oil, we're taking as much contaminants out of the system as we can. So engine oil pumps are positive displacement. Positive displacement means that if it's turning and it has a fluid on the inlet side of the pump, the only way to get through that pump is for that pump to turn. Kind of opposite of, or not opposite, they're both pumps, but if we look at our turbocharger, there is a passage for air to get through it when it's not rotating. So a pump that is positive displacement, it has to be rotating to get, in this case, our lube oil through it. That's what positive displacement means. They are gear driven and usually located in the crankcase close to the oil they pump. I would go a little further, and it may go further in saying that our lube oil pump is gear driven, and I mentioned off the crankshaft because that's where our rotational energy is coming from, is the crankshaft. So you can say anything that's being driven, rotated, is somehow connected through gears to the crankshaft. Oil pumps are driven either directly or indirectly by the engine gear train. In cases where the oil pump is located in the crankcase, the drive source is a vertical shaft and pinion engaged with a drive gear on the camshaft. That's less and less common. The bigger the engine you get into, typically our oil pump is just driven directly off of the gear train. We don't have any other long shafts connecting to the camshaft. Depends on where our components are located in our crankcase. A pickup assembly is located close to, but not in contact with the base of the oil pan. So our pickup tube is going to be, we want it pretty close to the bottom of the oil pan, but we don't want it so close to the oil pan that the oil pan is impeding the flow of lube oil into that pickup. So we want the pickup tube to have a bit of space between it and the oil pan, the bottom of the oil pan. And they give us a little illustration here in the PowerPoint I'm using. I'll also upload the PowerPoint that I'm using in this video, though I'm not going through each slide in order, and I'm not going over every one of the slides, but it's there for you to follow along with this, and then I would encourage you to look through each slide of this lesson, though I may not use the slide in this video. So there's our typical lube oil pump. Pretty common. That's called an external gear pump. We just very simple assembly. We have two gears that are within a housing, and those gears fit very tightly into that housing. They're able to freely rotate within that housing, but our gear teeth in this external gear design, the gear teeth contact the outside wall of the housing. So as these gears turn, our pickup tube is giving us inlet oil, or I'm sorry, I'm looking at it backwards here. The oil's coming in from the right-hand side, and as the gears rotate, that oil on the inlet coming from our pickup tube gets trapped between the wall of the oil pump housing and the gear teeth of the oil pump gears. Once these gears come in contact with the housing of the oil pump, it traps that volume of oil, however much oil is able to fit between the gear and the housing. And that oil takes a ride all the way around until we reach the outlet side of the oil pump. Both gears are doing this. So as the oil pump runs, we're constantly carrying oil around the outside of the gears and forcing them to the other side. An oil pump does not make pressure. An oil pump or any hydraulic pump makes flow. A restriction to that flow is what gives us the pressure. Anytime we're talking about any kind of hydraulics in general, whether it be lube oil, hydraulic oil, anything of the sort, we're always trading flow for pressure or pressure for flow. So in the lube oil system of a diesel engine, the oil pressure comes from the very small orifice where the oil is allowed to escape the pressurized circuit. Like I mentioned, around the main bearings, rod bearings, any of those moving parts within the engine. Once the oil makes it to those places, the way it's getting out is a very small space between those moving parts. This oil pump is providing enough oil to coat all those moving parts at but where we're pushing that oil out between those components doesn't allow for enough flow to get out of the outlet of the oil pump. Our main oil circuit, everything in the lube oil system is connected to this pump outlet. So however much that oil pump flows, if we don't give it free space for that oil to leave that inlet, if we don't have enough space for that oil to get out, that flow then begins to turn into pressure. Maybe to help drive the idea home, if you had worn main bearings, meaning we'd have more room between the main bearing journal of the crankshaft and the bearing surface itself. That is going to drop our oil pressure because we are giving that oil more space to get out. So the oil is going from the pressurized state when it makes it to that main bearing. Once it gets out the side of that main bearing and then drains back down to the oil pan, we have unrestricted that oil. So the pressure drops to 0 and our flow goes way up. Let's get back to what my slide has to say about this oil pump. External gear pumps consist of 2 meshed gears, one driven and the other within a housing machined with an inlet port and an outlet port. That's why I use these slides. So ultimately, our crankshaft is going to be driving one of these gears within this housing. And because that gear is enmeshed with the other gear in that oil pump, the gear being driven by the crankshaft drives the other gear in the oil pump. As the gears rotate, the teeth entrap oil and force it outside between the gear teeth and the gear housing to the outlet. Where the teeth mesh in the center, so right in the middle of the oil pump, where those two gears are enmeshed with one another, a seal is formed that prevents any backflow oil to the inlet. So, say we shut down the engine, because of these gears being enmeshed with one another, that creates a seal that will not let oil backflow. And then the oil can't get back around because the gears are in contact with the wall of the housing. There's some, just to kind of give you an idea of how tight the tolerances are in our oil pump. This is an illustration showing using a feeler gauge. You guys may have been introduced to a feeler gauge by Joseph. I'm not sure. I would assume you did. But ultimately, a feeler gauge is just a strip of metal with a given thickness, and we can get the correct feeler gauge for the amount of clearance we expect. And for instance, between the housing and the gear of the oil pump. And I could pick a feeler gauge that is 1/1000th thick, and that if that fits between the gear and the housing, that tells us if it's within spec. That feeler gauge should have a little bit of drag to it when you put it between the surfaces to be accurate. The reason you'd want to check that clearance is because if we don't completely seal that oil or trap that oil between the gear teeth and the housing, then we're not making as much flow, because now there is a way for that oil to not be pushed out the outlet. If we have leaks between the housing wall and the gear tooth. And in the other illustration, they're just using a straight edge across the bolt flange of the housing to measure the gear in the other dimension. That would be axial play in the gears, side to side within the housing. If any of those measurements are out of specification, if wear is going to cause a failure of the oil pump, it's going to be because those gear teeth have worn into the housing, or the end of the gear has worn into the oil pump housing, making a larger passage for oil to flow, which is going to bring our oil pressure down. There's another example that you may see in diesel engines or any internal combustion engines in general, is a gear rotor or an internal gear pump. And that's ultimately, we're still using two gears. We just switched to a ring gear and a gear within that gear. And they're at an offset, and we have an inlet and outlet. Not the external gear pump we just got done discussing is a more common pump. It's a simpler design. A gear rotor pump is usually found in smaller engine applications. But still, all the same things apply. With it's a positive displacement, so the only way through is for it to be rotating. It traps oil between the gear teeth to deliver it to the outlet of the pump. And no matter what style of pump we're using, the only way we get oil pressure is for the pump to make flow, and then we restrict that flow to get the pressure. Pressure goes down as our restrictions ease up, as our bearings wear, as the pump itself wears, and we get larger clearances between all of our moving parts, do we lose restriction and then ultimately trade our oil pressure for oil flow. I think in that first illustration I showed, I briefly mentioned a pressure regulating valve or pressure regulator. And that ultimately is so that we can have an oil pump that is capable of delivering more than enough pressure and flow, but maintain a set oil pressure that is desired by the original engineers who designed it. So, for example, if the system was designed to run at 60 psi of lube oil pressure, our pressure regulating valve would ultimately just bleed off oil from the pressurized oil circuit to bring us down to the target pressure. So if we're at 60 psi, that pressure regulating valve or pressure relief valve is ultimately just a spring-loaded valve that opens and drains some oil off of the main oil supply and back to the sump. The spring that is actuating that valve sets our pressure. So the more spring pressure there is on that pressure regulating valve, the higher the system oil pressure will be. So potentially a cause of a low oil pressure concern. If that spring in our pressure regulating valve fatigues over time or it breaks, there's going to be less force holding that pressure regulating valve closed, and it's going to open at a lesser pressure than our 60 psi, and it'll appear, or it won't appear, it will be a reading of lower oil pressure on system gauges. The pressure regulating valves are responsible for defining maximum system oil pressure. Most are adjustable. Typically, an oil pressure regulating valve consists of a valve body with an inlet sealed with a spring-loaded ball check valve. Other types of poppet valves are also used, which ultimately is a poppet valve or a check ball style valve. They're both spring-loaded, normally closed valves, meaning until we put oil pressure against it, the valve is closed. When the oil pressure exceeds the spring pressure that's holding that valve closed, whether it be a check ball or just a slug of metal that's sealing off that passage, as soon as our oil pressure exceeds that spring pressure, it pushes that valve open and allows oil to drain back to sump. So we're ultimately at the pressure regulating valve, we are trading that oil pressure that is above our 60 psi and draining off, so trading some of that pressure for flow and letting that oil flow back down to our oil pan. The regulating valve body is plumbed in parallel to the main oil pump discharge line. Ultimately, it's a branch back to the same place. So you have one passage from the oil pump outlet that feeds all of our main bearings, rod bearings, camshaft, rocker arms, all of our moving components, and then ultimately at the end of that circuit drains back to oil pan. And then we have our other branch off of the oil pump that goes to our pressure regulating valve. And it's just a shorter trip if the oil goes on the side of pressure regulating valve, because ultimately it comes right out of the oil pump. And if our system pressure goes above our spring pressure of the pressure regulating valve, the pressure regulating valve opens and our oil pump outlet begins to flow out of the pressure regulating valve rather than taking the other passage to lubricate our parts. When oil pressure is sufficient to unseat the spring-loaded check valve, it unseats, permitting oil to pass through the valve and spill to the oil pan or sump. This action causes the pressure in the oil pump discharge line to drop. The regulating pressure valve is adjusted by setting the spring tension of the spring, usually by shims or adjusting screws. So we can either have a screw that we tighten to put more preload on the spring, or where that spring is captured in the pressure regulating valve, we can add shims between that spring and the valve so that the spring is ultimately getting more preload as well, because we're compressing the spring. When we compress that spring further, it takes more oil pressure to overcome that spring force to drain oil back to sump. Oil coolers or heat exchangers is going to be rather adjacent to our pressure regulating valve circuit. It may be on the same branch as the pressure regulating circuit. And that's ultimately, we have our cooling system that manages heat of the engine to keep it cool. But we also get rid of heat through the oil, through the lube oil. Once the oil absorbs heat after it passes through the engine, we can use an oil cooler or heat exchanger to pull that heat energy back out of the lube oil before it goes back down to the pan to supply the oil pump again. Oil coolers are heat exchangers consisting of a housing and a cooling element or core through which coolant is pumped around which oil is circulated. So you can see in this slide of the PowerPoint, the first illustration here off to the side, labeled A, shows us the entire heat exchanger oil cooler. So we have basically two different systems interacting with one another. Our oil passes through what they have illustrated here in illustration B, just a bundle of tubes that are all sealed at each end so that oil can pass through those tubes. And then we put those tubes in the housing of the oil cooler, and the housing can flow cooling water or coolant for the engine. So as the oil passes through these little small tubes, we've got a lot of surface area that the oil is imparting its heat into. And then our coolant is on the outside of those tubes and is flowing. And the coolant comes in contact with all the surface area of those tubes and pulls the heat away. Just like pressure differentials, we have temperature differentials as well. If the coolant that's passing over our tube bundle in the cooler, if that coolant is 5 degrees cooler than our oil, heat is going to move from the oil to the coolant. If our oil temperature is 200 degrees and our cooling water is as hot as, just for an extreme example, if our cooling water coming through is at 198, that gives us a 2-degree temperature differential. So when that cooling water goes through our oil cooler, heat from the oil will move into the cooling water. Let's see, where did I leave off here? Oil temperatures in diesel engines run higher than coolant temperatures, typically around 110 Celsius or 230 degrees. However, the engine coolant reaches its operating temperature more rapidly than oil and plays a role in heating the oil to operating temperature. So they kind of go hand in hand. The coolant gets hot quicker, or the cooling water gets hot quicker. Now, this is in regards to a closed system. Ultimately, the cooling water system, the coolant can help bring the oil up to operating temperature quicker than if it were to not be in contact with one another. So, talking about a little bit of diagnosis or causes of failure here. And my slide brings up the possibility of these leaking. Either the tubes that hold the oil or that flow the oil, and the housing where the coolant is. If we have a failure of a seal anywhere within that oil cooler, now our cooling water circuit and our lube oil circuit are no longer completely isolated. If we get cooling water or coolant in the lube oil, we're going to start seeing bearing failures, main bearings, rod bearings, camshaft bearings, camshaft lobes, any of those moving parts. If we get our lube oil contaminated with cooling water, it can cause quite the damage. The inspection that my literature here is using for this oil cooler is to close off the housing and do a vacuum test. Basically, pull the whole cooler down into a negative pressure with it all sealed off, and seeing if you lose vacuum over time. So you pull it down into a negative pressure and seal it off and monitor it. If you lose negative pressure, then you know you have a leak between the cooling water section and the lube oil passages within that oil cooler. I'll go ahead and read their description here. Most OEMs prefer the bundles be leak tested by vacuum because this tests the assembly in the direction of fluid flow in the event of a leak. One header should be capped with a dummy plate and the other fitted with a evacuation adapter. So they're just ultimately taking that oil cooler, capping it on one end, capping it on the other end, but on one end we have a fitting that we can pull a vacuum. Lube oil jets or nozzles that spray oil. You can see in this slide, if you're following along, or if you can see it in my video, this particular example is a hook-shaped tube that actually taps right into the main oil gallery within the engine block and sprays oil up at the little end of the connecting rod and bottom of the piston skirt. And that does two things. It lubricates those components, but also is really effective in engine cooling. If we spray lube oil directly at the bottom of the piston, ultimately what we're doing is putting the oil in contact with a surface that is directly taking the heat as it enters the engine. Because on the other side of that piston crown is where our combustion event is happening. That's where the fuel oil is being burned and pushing on the piston. So we're putting our lube oil almost in direct contact with the heat source. So it's really effective. There's a very large temperature differential there. Our lube oil, maybe what they gave us earlier in the example of 230 degrees, but we're dealing with thousands of degrees of our combustion event. So we can pull a lot of heat out of the piston, through the piston, and back down to the oil pan sump. So we're spraying oil up at the bottom of the piston. It's gathering up a whole lot of heat energy, and then it's immediately just draining back down to our oil sump to further help dissipate that heat and ultimately run through the oil cooler and get out of the system. Piston oil cooling jets are a critical component of the engine lubrication circuit. They are plumbed into the cylinder block lubrication gallery and spray engine lube oil onto the underside of each piston to manage piston temperatures. So if it hasn't been exclusively said yet, the purpose of the lube oil system is to reduce friction between our moving components, the ones we mentioned earlier, like main bearings, rod bearings, wrist pins for the pistons, cylinder walls, all the above. We've got to reduce the amount of friction between those components to avoid premature wear. That is measured in coefficient of friction, which is the measurement of the aggressiveness of frictions between surfaces. Lubricants or lube oil are designed to reduce friction between surfaces that are or could be in contact with one another, creating wear at those contact points. Kind of going further into that, the functions of the lubrication system can kind of be broken down into these 5 bullet points of lubrication, sealing, cooling, cleaning, and protection. So to further kind of explore those bullet points, lubrication is reducing that coefficient of friction between components and ultimately preserving those surfaces and slowing down the wear that would occur if the friction were greater between those components. Sealing, we don't really think of oil being a way to seal something, but if we look at the characteristics of liquids, and you may have heard the terms of surface tension or capillary action of a fluid or of a liquid. And if we have components that are moving components that are tightly fit to one another or very close tolerances to one another, meaning there's not much space between those components. If the fluid that is in between those components is of the right viscosity and general characteristics of that liquid, in our case, lube oil, they can and will create a seal between parts. Next bullet point is cooling. We kind of mentioned that cooling property of the lube oil system when I went over our oil cooler or our oil heat exchanger, in that we pull heat out of the engine, that wasted heat or that rejected heat that comes from the combustion in the cylinders. The oil helps pull that heat away, and once that oil passes through the cooler, that heat from the oil is transferred over to our cooling system, and then the cooling system goes further to dissipate that heat into the atmosphere. Cleaning agent is our next point listed here for the functions of our lube oil system. And the cleaning agents kind of depends on what oil we're using and what blend of detergents and additives have been added to that lube oil. So the ability of the lube oil to clean is dependent on the additives that are in that oil, but also it helps when we have hydrodynamic suspension, is what it is called. In that, we were talking about that earlier when we talked about changing oil, in that contaminants are suspended in the oil, and ultimately we can get those contaminants out through our lube oil filtration system, because all our contaminants are suspended in that fluid, in that oil, and when that oil goes through the filtration circuit, those contaminants can be trapped by those filters. And then protection, that is protection against corrosion or oxidation, and ultimately kind of seals off those internal components from exposure to oxygen and moisture, which helps protect from those corrosion and oxidation. If we have corrosion or oxidation or debris, carbon deposits within the engine, that can accelerate wear as well. So our lube oil helps get rid of all that stuff so that our parts stay clean and free of corrosion, so that they can last as long as possible. And there's that terminology, hydrodynamic suspension. In hydrodynamic lubrication, maintaining a liquid film between moving surfaces is achieved by pumping lubricant through a circuit. The result is that the shaft journal floats on a film of oil, the thickness of which depends on the oil input and oil leakage rate. So I mentioned this when we were in person together last Monday. When we get that supply of lube oil to our main bearings, to our rod bearings, all those moving parts, the only time that we should have those surfaces in direct contact with one another. So, for example, the main bearing in contact with the crank journal, those two surfaces, the only time those should touch is when the engine is not running and that oil has a chance to drain back to the oil pan. During operation, we should have adequate supply of oil pressure to keep those two surfaces away from one another. So we have the crank journal surface and a film of oil, and then the bearing that supports it. If we keep enough oil pressure between those surfaces, no matter what other forces are imparted onto that crankshaft, that oil is able to keep the crankshaft suspended within those bearings, keeping those surfaces from wearing on one another. The thickness of the hydrodynamic wedge depends on the following four factors: the load increase, temperature increase, lower viscosity oil, and changing shaft speed. So we can have a change in that hydrodynamic suspension when any of these factors change. So if we have an increase in load on the crankshaft, whatever we're powering through this diesel engine, if that load increases, there's more forces acting upon the crankshaft and more force applied to that thin layer of oil that could potentially push that thin layer of oil out and back to the sump, which is what we don't want. We don't want that oil being pushed out, because then we're having metal on metal contact, which leads to the wear. Temperature. The hotter the lube oil is, the thinner it gets, the thinner the viscosity gets, and the easier it is for those forces to push that oil out between those surfaces. So that's why it's important to manage the temperature of the engine. And then the changing shaft speed. So centrifugal force plays a role in slinging the oil away from those rotating parts. So all these things have to be taken into consideration when the engineers are designing the overall engine, and then the lube oil circuit that is going to supply adequate lubrication for all the moving components without getting excessive wear, so that that engine can last a decent amount of time before overhaul. Here's the kind of an illustration that you'll find in that PowerPoint that I uploaded. I'm uploading to Blackboard, and this kind of gives us a relationship, the math between the hydrodynamic suspension and how the oil film keeps a barrier between those two metallic surfaces. You guys can look at that closer in the PowerPoint. Trying to move quickly so that we can cover as much as we can here. And again, forgive me for my awkwardness in this format. Not used to talking to a camera with nobody in the room. Oil contamination and degradation. So these are the things that ultimately require us to change the lube oil every so many hours, so many miles, however we're keeping up with the in-use period of that oil. And contamination and just that oil breaking down over time during operation is going to determine the life of that oil. But some of the things that can contaminate the lube oil is fuel, engine coolant from our cooling system, oil aeration, so air getting in to the oil, and then sludge production from contaminants in the oil and the temperature that the lube oil is exposed to. You say, how do we get, or how could we get fuel contamination in the lube oil, and why is that a problem? So where does our fuel come from? It's ultimately, the only place we should have fuel in the engine is in the combustion chambers, but we're not always running at 100% efficiency. As the piston rings wear, we lose the efficiency of those piston rings to seal the piston to the cylinder wall. And ultimately, over time, the result of that wear is some of that fuel that is injected into the cylinder makes it past the rings, and ultimately, once it's past the rings, we're down where the rotating assembly is, and ultimately oil pan or oil sump. So unburnt fuel or fuel that has made it past the piston rings ultimately makes its way into the oil pan to contaminate the oil. Why is that a problem? Well, when we add fuel oil to our lube oil, it degrades our viscosity of that oil and the surface tension of that oil, and the ability for that lube oil to its hydrodynamic suspension capabilities are reduced the thinner that oil gets from that contamination of fuel, or any other of the contaminations that we'll talk about are going to reduce the viscosity of that oil, and ultimately reducing the oil's ability to keep that crankshaft from contacting those bearings. Coolant is another contamination that we can get. Usually that's a pretty substantial problem there if we're getting coolant in the oil. Unlike fuel getting into the oil, we're going to have some fuel get into the oil, just like I described, getting past the piston rings and so on. But if we're getting coolant in the oil, we have somewhere within the engine or in a cooler, like I talked about earlier, where there is a passage between the oil and the cooling water. So ultimately, that's going to be something that needs to be diagnosed as to why there is cooling water or coolant getting in the oil. which does the same thing as the fuel. It reduces the viscosity of the oil, and ultimately we end up with wear from friction between parts because the oil is not able to suspend that crankshaft or that camshaft on that oil because it's just not, it doesn't have the surface tension that it should. And all the forces that are imparted onto the crankshaft or the camshaft are able to overcome that thin layer of oil and push that oil out and make contact between the bearings and the shafts. Oil aeration, that's also another fault. That's not a normal engine operation thing. If we're getting oil, air in the oil system, then we have a leak somewhere. Typically, if you're getting air into any kind of hydraulic circuit, ultimately it has to be almost always a leak on the suction side of, in this case, the oil pump. So where is the suction side of the oil pump? We're talking about the pickup tube in the oil sump or in the oil pan, where the oil pump sucks up our oil. If we have a leak there in that pickup tube, ultimately, as the oil is sucked up into the inlet of the oil pump, if we have a leak in that pickup tube that is exposed to air, it can pull air into the inlet of the oil pump. Then once it gets in the oil pump, we get air mixed in with the oil. Same thing as contaminated with fuel or coolant, in that it reduces the oil's ability to suspend those parts and keep a thin layer of oil between those metal parts, which ultimately results in accelerated wear. And then sludge, that's a result of, temperature, as we mentioned earlier, but that's also contamination issues as well, where the oil is reacting with some other chemical that's in it, or the oil is breaking down over time, the molecules of the oil through heat and pressure and all these other contaminants are going to degrade the oil. I will say one other thing before we move on from oil contamination is that we can get essentially water contamination into the oil through condensation. So as the engine heats up and cools off, just like condensation on a glass of water, as we go through those temperature cycles of up to operating temperature, back down to ambient temperature, depending on what the ambient temperature is going to determine how much condensation forms on the inside of the crankcase. The more condensation that is built up inside the crankcase, the quicker the oil gets contaminated with water. And ultimately, if it's not monitored and kept up with, can lead to accelerated wear of all of our internal components. Quickly looking through, looking for things that are relevant to what we're talking about here. You guys can look at these more in-depth slides on oil viscosities and the grades of oil, what the numbers mean. 15W 40, 10W 30. That is, the numbers represent the viscosity rating of that oil. And if we have in this example, 10W 30, the 10 would be, the W stands for winter. So at cold temperatures, the viscosity is that number. But the second number, the number to the right, in our example, 10W 30, 30 is the number I'm talking about now. That is the viscosity number at operating temperature. So you guys have a look at those slides if you've got the time for it. It is valuable information that will help your understanding of engine systems. I'm just not gonna go too far in depth with it here. Synthetic oils, the only thing I'll touch on with synthetics versus conventional oils is ultimately that's how the oil is made and what the oil is made out of. A common characteristic when we compare synthetic to a conventional oil is that some of you may have heard of, hey, don't change to a synthetic oil, it'll cause oil leaks. That is not the case. There is a behavior of that oil that has kind of fueled that idea that you will get leaks from switching to synthetic. It's not that. It's that if you have existing leaks in an engine that's running conventional oil, and then you switch it over to a synthetic oil, that leak will appear to be worse. And the reason for that is we stuck both oils up under a microscope. We would find that typically in a synthetic oil, the molecules of the oil are smaller in a synthetic oil than they are in conventional. So when we do have a leak, that leak appears to get worse because on a molecular level, synthetic oil has smaller molecules, so it's able to get out of that leak quicker, ultimately appearing to be making the leak worse. We get into oil filtration. There's many different architectures and designs of oil filtration circuits. And what we've got listed on our PowerPoint here is full flow or bypass. Full flow means that the oil filtration is in series between the oil pump and the lube circuit. Bypass is ported off a lube gallery in parallel. So easy kind of how to differentiate between those is in a full flow, the filter, the only way we get lube oil to our crankshaft, to our camshaft, to our rocker arms, to our cylinder walls, to the cooling jets, to anything that needs lube oil, it has to go through our filtration. And that would be a full flow, and that means it's in series. A bypass ultimately means there's two paths for the oil to take. Kind of like I was talking about with our pressure relief circuit, in that out of the oil pump, we can go to our lube oil circuit and lubricate all of our internal components, or the oil can go on a different path and go through the filtration circuit. The term positive filtration is used to describe a filter that operates by forcing all the fluid to be filtered through the filtering medium. So if you hear the term positive filtration, that is, I would relate that to a full flow system where oil has to go through the filtration to reach our lubrication circuits. And in the PowerPoint, you'll see a couple different types of filtration methods. We've got a mechanical strainer that's similar to what you find on the end of the pickup tube. It's just going to catch all the heavy, larger debris, and that's just ultimately a screen, a steel mesh screen would classify as a mechanical strainer type filtration. Absorbent filtration or adsorbent filtration is the other types here. Let me get caught up in my book here. Maybe. Absorbent filtration work by absorbing or sucking up engine contaminants as a sponge would. So absorbent, you can think of a sponge. It sucks up those contaminants like a sponge would. Effective absorbent filtering media include, absorbent would be cotton, pulp, mineral wools, wool yarn, and felt. These filters not only absorb coarse particles, but may also remove insoluble oxide, particulate, moisture, and acids. Our other type, the adsorbent filtration, is filters adsorb by holding or by adhesion the molecules of dissolved substances or liquids.